Welcome. In this video, we're going to complete the Comparing Two Means practice lab. Here's the scenario. The data for this assignment were generated from Mrs. Mitchell's algebra class. The students in this class performed poorly on the school-wide geometry readiness test. So they reviewed the material over the next week and took the exact same test a second time. A gender variable is included in the data set as well. To complete this assignment, conduct the appropriate analyses. Paste the relevant SPSS output into your Word document and answer the questions. In order to complete this practice lab, you need to download the Word document, Comparing Two Means Lab Practice. You can open this up in Microsoft Word or in Google Docs or in many other word processing programs as well. You'll also need to download and open the SPSS data file called mathscores.save, which is available to you as well. Let's take a look at the data set before we jump in. Some of you may be new to SPSS, so I'll point out a couple of features and highlights to help orient you to the software program as well. In this data set, we have three different variables. So I'm switching between the data view and the variable view. And we're within the data editor window. So here in the variable view, we see that there are three different variables. Pretest, and this variable is labeled scores. There we go. This variable is labeled scores from the first time the test was administered. So these are kids, high school kids, and a math class. So they're in high school, they're in a math class, they're taking algebra, and the teacher, Mrs. Mitchell, is trying to get them ready for geometry. So there's a school-wide geometry test. It's standardized, and everybody takes it before they move on. So these are the kids' scores from the first time they took that test. Pre-test. Post-test, these are the scores from the second time the test was administered. Right? So remember, she gave the test. They didn't do well. She reviewed the material, and they gave the test again. Okay, so we have before and after she reviewed the material. It's the scores on the same test for the same kids. And then finally, we have a gender variable. Now, gender is a categorical variable, right? It's a dichotomous variable. It's either male or female. So this has been coded 0 equals male and 1 equals female. So there are different types of variables in SPSS. You could have a numeric variable, that's a number value. Right? You could have money, you could have a date. You have what's called a string variable. This is where you write out a word. In this case, even though male and female are words, we're using numeric variables which have been coded. 0 equals male, 1 equals female. So we can use a numeric variable, right? A numeric variable type in order to represent categorical data. There are only two groups, 0 and 1. We go over to the data view, we can see the actual data for these students. So we're going to simplify this activity so you can learn the processes. So there's only 16 individual students in the data set. So in this, in the data view, every row is a participant, every column is a variable. In the variable view, every row is a variable, so they're arranged differently. Here you have the actual student. So this is the first student, second student, third student. There doesn't happen to be an ID variable. Oftentimes you'll see an ID variable first, or one of the first variables. You could 1, 2, 3, 4, 5, student 1, student 2. You could have the names of the students, Ricky, Bobby, Susie. But here there's no ID variable. We just have the data for each student. So there's 16 students, 1 through 16, and there are three pieces of information for each student. So this first student in the data set scored a 57. We don't know what the score is out of this one. Looks like it goes over 100, so they're not percent. So there's some sort of raw score, perhaps, or a scaled score of some kind. So the first student scored 50% the first time. After they reviewed in class, they scored 87%, and this is a female. You can toggle between the codes, the numeric codes, and then the values in this coded variable gender, like this. So first student has a 1 for gender, which we know equals female. Okay. Again, these two are ratio level variables or scale level variables in the variable view. We go to the end here. So the type of measure, these are scale. That means that the There's an order, right? Someone who scores a 50 has a higher score than someone that scores a 40. And it tells us that the intervals between values are equal. So someone who scores the difference between 40 and 50 is the same as the difference between 50 and 60. Down here we have a nominal or categorical variable for gender, right? So it's a grouping variable. 1 is not higher than 0. We arbitrarily chose 1 to represent female and 0 to represent male, but these aren't in order. This is not an ordinal variable because 1 is not higher than 0, in contrast to the test scores where 1 would be higher than 0. All right, let's go back to the lab. Part 1. So there are 3 parts to the lab: Part 1, Part 2, and Part 3. We're going to be comparing means, and we're going to be using a t-test. But there are 3 different types of t-tests that we're going to be looking at. And each type of t-test is useful and appropriate in a slightly different situation. All of them will compare 2 means, but they each do it in a slightly different way. So each part of the assignment will let us try out a different t-test. So each part of the assignment has a slightly different situation. They're all related to this algebra class, but they have a different aspect of the problem, and that different aspect means that we're going to use a different type of t-test. So we'll focus on that. Part 1. Mrs. Mitchell is disappointed with her students' performance on the geometry readiness test. That's the pretest variable. So she begins with just this information. She doesn't like what she sees. She knows that the school average for the test is 85, and she fears that her students have performed significantly below average. Mrs. Mitchell wants to know if there is a significant difference between her class and the rest of the school. So we have a mean for her students. We haven't calculated that mean, but there is a mean for these students at pretest before they reviewed. There is a known mean for the school. The school average is 85. This is not as common of a situation because typically the population mean is not known, but sometimes it is. So in this case, it's given to us that the population mean is 85, and we want to know if the mean of her students is different from 85. Right? Are they on track with the rest of the school, or are they off track? So we're going to begin by stating the null and alternate hypotheses. The null and alternate hypotheses. Typically, the null hypothesis is that there is no effect, right? That there's no effect if we're using an experiment, or in this case, it's not experimental yet. We're looking to see if there's a difference, right? So no effect or no difference is typically the null hypothesis. If it's a correlation, it could be no correlation. And the null hypothesis, the alternate hypothesis, is some kind of an effect, some kind of a difference that we're going to be able to detect. Usually we want the alternate hypothesis to be true. If we have an experiment and we try a new experimental drug to decrease tumors, we'd want to see a difference with that drug, but it's not always a good thing. So here, it sounds like she wants her students to be on par with the rest of the school. She's concerned that they're not, so we, in a sense, would prefer not to find a significant effect here. So the null hypothesis is going to be that there's no effect or no difference. In other words, that the mean of her class is not different, right? No difference from the school average, which is 85. So you can write hypotheses using formal scientific or mathematical notation. As we begin the process, I'm going to write it in plain language. It might help you conceptually to understand what we're trying to do. So the null hypothesis is that the mean of Mrs. Mitchell's class at pretest is 85. And I picked 85 because that is the known population mean. She knows that the school average for the test is 85. So when we say there's no difference or no effect, we're saying that the mean of her class is 85. That's the null hypothesis. There's no difference between her class and the rest of the school. In this case, that would be good news because she's worried that they're falling behind the rest of the school. Right? She's worried that there is a difference. Now, our alternate hypothesis is going to be that there is an effect or there is a difference. There's something called a unidirectional hypothesis and a bidirectional hypothesis. A unidirectional hypothesis specifies whether the difference, which direction, right? This is also can be called a directional hypothesis, which direction the difference is going to be in. My class is below 85, right? Less than 85. Or perhaps she thinks her students are doing quite well, and my class is above 85, greater than 85. So you could have a directional hypothesis. You could also have a bidirectional hypothesis. It could go either way. It could be that the mean is higher. It could be that the mean is lower. But the key is that there's simply a difference between the two groups. Now here, she does have an inkling that her students have performed below average. But for simplicity in our labs, what we're going to do is we're going to use bidirectional hypotheses. We're going to state that her class, the mean of her class, is just simply different from 85, that it's not 85. When you test the hypothesis statistically, the process is just a little bit different. When you have a unidirectional hypothesis, you have more of what's called statistical power. Basically, you take that p-value, and the p-value tells us the level of significance, and you cut that p-value in half, which means you get twice as much statistical power, which technically you can do. The problem with this is that you have to convince your reader, because you're going to report your findings. You have to convince your reader that you really did hypothesize that the difference was going to be in that direction. Because if the significance is very close, right, it's just beyond that threshold of statistical significance, somebody might think that you really didn't have that hypothesis ahead of time. You just simply thought they were going to be different. You didn't know which direction it was going to go. And after you found that it wasn't significant, you said, I'll just tell people that I had a unidirectional hypothesis, and so that you can have report statistical significance. So people will sometimes be suspicious of that. So it's safer, it's more conservative to simply use a bidirectional hypothesis and state that it's going to be different. So that's what we're going to do here, but just simply be aware that that is something that some might do and arguably could be done in this situation. In this case, we're going to use a bidirectional hypothesis, simply state that the mean is different. So the mean of Mrs. Mitchell's class is not, at pretest, let's clarify, is not 85. It's different from 85. It's statistically not 85. This notation here, this is H sub 0, which is the notation for a null hypothesis. This is H sub A. The A stands for alternate. Sometimes you'll have more than one hypothesis to test, and you'll have H sub 1, H sub 2, H sub 3, and so forth. Or sometimes even with one hypothesis, you'll just see H sub 1. So two different types of notation you may see here. So the null, right, no effect, no difference. The mean is the same as the rest of the school. It's 85. The alternate, there is a difference. The mean of her class is not the same as the rest of the school. In other words, it's not 85. So which kind of t-test should Mrs. Mitchell use for this analysis, and why? Let's review the three different types of t-tests that we have to choose from. This is one of the most difficult parts of learning statistics, is knowing which type of test to run. Running the actual test, especially when you're using SPSS, is very easy. You just click on a couple buttons and the output comes up. The parts that are difficult is knowing which test to run and then being able to properly interpret those results. The actual button clicking is pretty easy, and I'll show you that. But first we have to decide which type of test to use. And students have a lot of trouble with this traditionally. So our three types are the one sample t-test. Right. I'm going to write them right here. I'll delete the ones we're not going to use, but just to illustrate. So we have a one sample t-test. We have a two sample t-test. This is also called an independent samples t-test. And then we have a dependent samples t-test. Oops. Dependent. Also called a paired samples t-test. So two of these have two different names. So one sample t-test, this is a situation where you have, just like it sounds, one sample. So you might think, well, wait, we're comparing two means. How can you compare two means if you only have one sample? Right? You have one mean to work with. Well, this is because you have a known population mean. You're comparing it against a number of value you already have. So I know, for example, let's say we're dealing with IQ, and I wanted to know if the IQ of the students in my gifted and talented class is different from average. Well, I know that the population mean, that population average is 100. That's how IQ tests are normed traditionally. So I want to see if their mean, right? So I calculate one mean for this class is different from the average for the population, which is 100, right? It's a one sample t-test situation. Next, we have the two sample t-test, and this is a situation also called an independent samples t-test because you have two different groups, two different samples, and they are independent of one another. It's not the same people being tested twice, or at least, I should say, the scores are not paired up between the two different groups. So this would be a situation where you have perhaps an experiment where you have a control group and a treatment group. This would be a very good example of that. So you're testing out a new drug. You're trying to reduce tumor size. You have you randomly assign participants to two different groups, a treatment group and a control group. And you give them all, either the treatment group can have the drug and then the control group can receive a placebo. You take measurements after a certain period of time, let's say after 6 weeks. And now you're simply comparing the size of the tumors in the control group with the size of the tumors in the treatment group. This is an independent samples t-test, or a two samples t-test. Finally, we have a paired samples t-test. This is where you have two means that you are comparing. You have two samples, but they are paired up. They are dependent on each other. They're not independent. And the best example of this is a pre-test, post-test situation where your participants serve as their own control group. So you have perhaps a weight loss program, and you weigh everyone, see how much they weigh at pre-test. Then you put them through your weight loss program. Let's say it's an 8-week program. And after 8 weeks, you weigh them again. And you want to see if the weight of this particular group has changed over that 8-week period. If it's different than it was before, and you wrote down the person's name. So when you weighed Tom, he weighed 180 pounds at the beginning, and he weighed 170 pounds at the end, right? You know that both scores belong to Tom, and you match them or pair them up. This is a paired samples or dependent samples t-test. So for each of these parts, we're going to look at the situation and see which category that falls in to know which type of test to use. So how many samples do we have here? We have her class. They've only taken the test once at this point, so all we have are these data in the first column. We don't have these data because they haven't taken the second test yet. We have one sample, one mean. Well, we're using a t-test, right? We're comparing means. So what's the other mean? Well, it's the school average. It's a known population mean, which is 85. So we're going to use a one sample t-test because we have one sample, one mean from our kids, comparing that to a known population mean of 85, one sample t-test. I'm going to go ahead and delete the other ones, and we will put that in here. So Mrs. Mitchell should use a one sample t-test. And why, right? Which type of test? It's the first thing is knowing which test to use, but also being able to explain why that's important. Because she is comparing the mean of a single sample, I have a little trouble writing here, of a single sample to a known population mean. Okay, that's why she's comparing the mean of a single sample, her class at pretest, I think I was capitalizing that, to a known population mean, the school average of 85. Okay, that's why we're using a one sample t-test. Next it says run the analysis and paste the output here. So let me show you how to do that. It's not too difficult. There is one tricky part. So we're going to go to Analyze, Compare Means. Let's take a look here. So we have a few different options under the Compare Means category. We have the one sample, among others, we have the one sample t-test that we're going to use right now. We have the independent samples t-test, that we talked about, and we also have the paired samples t-test that we talked about. This right here, one-way analysis of variance, this is used for something else. We're going to focus on these three different types of t-tests. So we're going to click on one sample t-test. So analyze, compare means, one sample t-test. Let's click on that. Okay, so the easy part, you have to tell the computer which variable you want to test. So what's the sample that you want to compare? Well, we want to compare the scores from the first time the test was administered. That's pre-test. Don't include anything else, just the scores the first time the test was administered. Now, here's the tricky part. This is what students have the most trouble with. So when students do poorly on the independent practice, this is the mistake they most commonly make. So please pay attention. You have to tell SPSS the test value. This is the known population mean. So again, you're comparing the mean of your sample to a known population mean, which is, in this case, the school average of 85. Don't leave this at 0. This is the most common mistake students make when they run a one-sample t-test. They forget to put in the test value. They leave this at 0, which is the default, and when they do that, they end up comparing the sample mean to 0. If you were to do that, you would find very strongly significant results, because the population, or the sample mean, excuse me, is way different from 0. Right? This isn't anywhere close to 0. So you're going to come out with very highly significant results and report that, but that's going to be misleading because the population mean is not 0, it's 85. So you have to put 85 into this box, into the test value. You're going to have a question like this in the lab assignment. Will you complete that independently? So pay attention. Look closely at the description to see what the population mean is, and make sure you put the correct value right here. If you end up with a p-value of 0.00000, it could be that even with the correct data, it's that statistically significant. But it also could be that you forgot to change it. You're comparing your sample to 0 and getting inaccurate conclusions. Now we're going to click OK. Your output consists of two different tables. The first one is one sample statistics. This tells us that the n, or the sample size for this variable, is 16, which makes sense. The mean is 72.63, so we had not yet calculated that. So that's the mean of these numbers right here is 72.63. The standard deviation, 13.251, and the standard error of the mean, 3.313. Now down here is the results from the t-test. So this is just descriptive statistics up here. Down here we have the results of the inferential statistics, the statistical analysis we ran, which is the one sample t-test. The t-value, now this is comparing, now look right here, the test value is 85. So double check to make sure that you have 85 right here. If you don't, if you have 0, that means you didn't change it to where it should be. Also, when you complete your independent practice, again, make sure the test value is what you thought it would be. If it doesn't look like the answers are right, that could be what happened. So your test statistic is 3.736. The degrees of freedom is 15. That's the sample size minus 1 because it's a one sample t-test. The significance level, this is a two-tailed test. Two-tailed because this is a bidirectional hypothesis, right? Our hypothesis is that the mean is not 85. It's higher or lower. If we were to run a unidirectional hypothesis, if we had said the mean is just less than 85, we would actually end up cutting this in half. It'd be 0.001 instead of 0.002. Either way, it's significant, doesn't really matter. The mean difference is 12. What this means is that's the difference between 85 and 72. And the rounded. And then this is the 95% confidence interval of the difference between the mean. So the estimated difference between the mean is 12, but it's somewhere between 5 and 19, right? But since this interval, -5 and -19, since this interval does not include 0, it is significant at an alpha level of 0.05, which is kind of the default most people use most of the time. So what we're going to do is we're going to copy this output over here into our document. Now right now I have this open up in Google Docs. It's a little tough to copy and paste directly into Google Docs. You can bring it over as text if you want to. The problem with that is it's a little hard to read. You can see how it kind of gets crunched and it doesn't line up nicely. So what I'm going to do instead, I'm going to open this up in Microsoft Word because it has better copying and pasting capabilities. So I downloaded this to the computer in Word format. I'm going to go ahead and open that up. So everything's the same. It's just going to allow me to copy this as an image, as a JPEG file, and drop that over here into my document. And there it is. It lets me resize it, move it around, format it, and everything's lined up nicely, right? If I just copy it as text, it gets mixed up. So I right-clicked, hit Copy Special. I leave my default as image for that reason. The original default might be something like that, but you can change it. If you put it on image, click Save as Default, and then over here I right-clicked and hit Paste. So you can, it doesn't matter if you keep the source formatting or not because it's a picture. If you're using Macintosh, so I'm using a PC for this illustration. If you're using Macintosh, sometimes users have a little bit of trouble with that. It doesn't allow them to copy it straight over. If that happens to you, there's one option is to do a screenshot. Take a screenshot. If you're not sure how to do that, go ahead and just Google that, taking a screenshot on a Mac to find the correct process for your operating system. You can paste the screenshot and then crop it down to the table. Let me go ahead and add a little border around that so that this information is what displays in your document. Okay, let's move forward. Based on your analysis, how did Mrs. Mitchell's students compare to the rest of the school? Will you reject or fail to reject the null hypothesis? So the null hypothesis is that the mean is 85. That's what we tested here. We tested whether the mean is 85. So if and whether the mean is significantly different from 85. So here we find a significance level of 0.002. So this means that we would have a 0.2% chance. So I move the decimal place 2 places over, a 0.2% chance of finding a test statistic at least this large if the null hypothesis were true. So if the mean of your class really was 85, then it would only be a 0.2% chance we would generate this test statistic. Our cutoff is 0.05, or a 5% chance. So what we say is we have evidence here, strong evidence, that the mean is not 85. It's very, very unlikely that the true mean of our students is 85 based on the data we have in front of us. So because we have such strong evidence that the mean is not 85, we're going to reject the null hypothesis in favor of the alternate hypothesis, that it's different from 85. We haven't proven that it's different from 85. But we have strong inferential data, strong inferential findings that it is different. So let's go ahead and report that, and we're going to use APA conventions to do so. So let's see here. Mrs. Mitchell's students scored significantly, and in this case, below, right? So it was different from 85, and it was more specifically, significantly below 85. So her students scored 72.63. So that's less than 85. Scored significantly below the school mean, comma, space, in italics the letter T, because it's a t-test. In parentheses is the degrees of freedom, which is 15. Space equals space. The test statistic, 3.7. I'm going to round to the hundreds place, 3.74. You don't need to include the negative. It's okay if you do, but it's not necessary. This is an absolute value. It's only negative because in our case, our mean was below the test value. If it had been higher, it'd be positive, but the p-value will be the same whether it's positive or negative. So you can just simplify your reporting by not including the negative. Comma, space, in italics, the letter P, space, is less than, and we're going to report this relative to the next highest cutoff point, which would be 0.01. So space 0.01, period. So here is the way we would report this in APA format. Nowadays, people are starting to report it to 3 decimal places and just put p equals. So p equals 0.002. I'm going to use this traditional convention in this lab, but be aware that you'll see that from time to time as well. So Mrs. Mitchell's students scored significantly below the school mean. Here's how we would report that using APA format, giving our reader all of the data. You could also report an effect size. So we could calculate, we could look at the standard deviation, which is 13.25, and calculate the effect size as well. Let's go ahead and do that. So the difference between the mean and between the two means is 12.375. I'm going to divide that by the standard deviation of 13.251, which gives us an effect size of 0.93. So that's a large effect. When you're interpreting this, something around 0.2, that's a small effect. So if we had seen an effect size of 0.2 right here, then we would say, yes, she might be below the mean, but not by very much. 0.5 is a medium effect. 0.8 and above is a large effect. So her students are well below the mean. This is a both significant difference and a statistically significant difference, as well as a practically or substantively significant difference. Okay. We can actually add that here. So we'll just add a comma and a space. A D in italics equals 0.93. So this tells our reader that we have a statistically significant difference and we have a large substantively significant difference. Finally, it asks us, will you reject or fail to reject the null hypothesis? So the null hypothesis is that the mean is 85 and the alternate is that it is not 85. So here we have tested this. We have found strong evidence. P is 0.002. That the mean is not 85. Therefore, we will reject the null hypothesis. Excellent. Let's move on to part 2 of the assignment. So after reviewing the material, Mrs. Mitchell gives her students the same test again. So she sees that they're having trouble. Her solution is to study. Let's go over everything. Let's review it all and see if we can raise the students' scores and get them ready for geometry. So she gives her students the same test again. These are the post-test scores right here. So first we analyze the pre-test scores. Now they've studied and they've taken the test again. These are the post-test scores. She wants to know if there is a significant improvement in scores between the first and second administration. What are our null and alternate hypotheses? So our null hypothesis is typically that there is no difference or no effect. So the null hypothesis is that the scores at pretest are the same as the scores at post-test. They're the same, there's no difference. The alternate hypothesis, again, we're going to use a bidirectional hypothesis for simplicity, is that the scores at pretest are different from the scores at post-test, or that they are not the same. Okay, so they're the same, they're not the same. What kind of t-test should Mrs. Mitchell use for this analysis, and why? So again, 3 different types of t-test to choose from. Your one sample t-test, you have one set of data you're comparing against the known population mean. That's what we did in part 1. You have an independent samples t-test where we have 2 different groups that are not paired up in any meaningful way. Well, we do have 2 different samples, 2 different groups here, but they are paired up. We have pre-test and post-test. For each student, we're looking to see, so let's say this is Johnny. Johnny got a, oh no, this is a female. Let's say, well, I guess that could be a girl's name. This is Johnny. So we have, she got 57 before, and now she got 87. So we're looking at her new score compared to her old score. So these are not independent of one another. So this is going to be the third type, which is our paired samples or our dependent samples t-test. Mrs. Mitchell should use a paired samples, also known as dependent samples t-test, because she is comparing the same students' scores from before and after. Their pre-test scores are paired with their post-test scores. So that's why we're going to use a paired samples or a dependent samples t-test. What if they hadn't written the students' names down, if they hadn't kept track? They gave everyone the pre-test and it was anonymous, and then they gave everyone the post-test and it was anonymous. Well, then you wouldn't be able to pair up the scores and this wouldn't work. This only works if your data set looks like this, where for each person you know their score at both times. Okay, run the analysis in SPSS and paste the output here. So we're going to go to Analyze, Compare Means, Paired Samples t-test. Analyze, Compare Means, Paired Samples. The dialog box looks a little bit different than it did before for our one sample t-test. What it wants to know are the two variables that are being paired. So we're going to put the scores from the second t-test in the first variable box, the scores from the first t-test in the second variable box. The order really doesn't matter. It's going to subtract this one from this one. So if we're expecting to see a gain and you organize it this way, then you're going to get a positive test statistic, positive t-value. Otherwise, you get a negative t-test value. But it really doesn't matter. You'll just report it without the negative sign if you go that direction. Everything else is going to be the same. So don't get too hung up on that. The important thing is that they are paired together, the two correct variables. Gender should not be used anywhere in the analysis at this point. And we're going to click OK. Out comes the SPSS output. So we have descriptive statistics first. So the scores from the first time it was administered was a 72.63. I'm going to go open this up so we can see this a little bit better. 72.63. We already knew that, right? It should be the same as what we had before. The mean from the second time the test was administered was an 80, roughly an 82. So scores went up about 10 points. More specifically, they went up 9.25 points. So the scores went up about 9 points. Right, our sample size is 16 both times. We get the standard deviation. It's slightly narrower the second time around. So this is good. So far, so good. But this doesn't mean they have improved significantly or statistically significantly. It just means the observed mean is higher. Of course, if it were about the same or lower, we'd really be in trouble. But this is what we're looking for. We want to see an increase. Here we have the correlation between the two. We don't really need this for this analysis, but in case you're interested, there's a correlation of 0.6 between the two sets of scores. And then here is the statistical output. So I'm going to copy and paste this into my document. So based on your analysis, how did Mrs. Mitchell's students' performance change between the first and second test administration? Will you reject or fail to reject the null hypothesis? So let's take a look over here. It's slightly larger on the screen. So the mean difference is 9. So they went up by about 9 points. The standard deviation is 10.517, so it's just under a standard deviation. We can calculate that effect size, but we can tell already if it's about a standard deviation, it's going to be large. So far, so good. Over here, the confidence interval of the difference is between 3 and 14. It does not overlap 0, so another good sign. The test statistic is 3.518. Degrees of freedom is 15. Sample size -1. And because it's a paired samples t-test, and the significance level is 0.003. So because this p-value is less than 0.05, we have statistical significance. So this is great. That's exactly what we're hoping to see. So Mrs. Mitchell's students scored significantly higher at post-test than they did at pre-test, comma, space. T in italics, the degrees of freedom, which is again 15, in parentheses, right? Space equals space. So pay attention to these tiny details. Let's see here. The test statistic is 3.5. I'm going to round to the hundreds place, 3.52, comma, space. P in italics, space, is less than the next highest cutoff point. Since this is 0.03, the next highest cutoff point would be 0.003 would go up to 0.01. Should we calculate the effect size? Why not? So we're going to look at the difference between the means, which is 9.25, divided by the standard deviation, which is 10.517, which gives us an effect size, we'll round it to the hundreds place again, of 0.88. D equals 0.88. So this is, again, because it's over 0.8, a large effect. So before they were well below average, now they've improved significantly, statistically significantly, because P is less than 0.05, in fact, is less than 0.01, and substantively significantly, because our effect size is large. So the students are doing better. That's good news for Mrs. Mitchell. That's almost certainly what she's trying to accomplish. Finally, Mrs. Mitchell wants to know if there is a gender difference in her students' performance at post-test. So we're talking about the scores at post-test right here. We're not looking at the pre-test scores anymore. We're only looking at the post-test scores. However, she doesn't have any particular reason to suspect that one gender will score higher than the other. So this is interesting. She just wants to know if the boys or the girls are doing better in the class. Why might she be asking this question? Well, it could be, it could be that maybe on average, the boys have been doing better school-wide. Typically, boys tend to score a little bit higher in math. Girls tend to score a little bit higher in language arts. So maybe she's wondering, is this pattern existing in my class? Maybe she was worried about that, and so she gave the girls a little extra support, a little extra encouragement. Maybe she was resisting some of those stereotypes about girls not being as good at math that we find in the United States from time to time. And so she thinks it should be fine, but I just want to check and see. Maybe someone accused her of favoring the female students. And then one of the boys said, well, you're always nice to them and you give them extra help and you're not helpful to us. Who knows? But for some reason, she's wondering about this, and she wants to test and see if there is a gender difference at post-test. Okay? So we're going to be comparing the boys and the girls' scores at post-test. I'm going to go ahead, I'm going to put these in order. I'm going to group these, male and female. So we're going to be comparing the boys to the girls. So these scores compared to these scores. These are no longer in here. Right, these are done with. We're just comparing these, this mean, the mean for the boys, to this mean, the mean for the girls. Okay? So the null hypothesis is no difference, no effect. So the boys' scores are equal to the girls' scores. They're the same. What's the alternate hypothesis? Well, it's some kind of difference, some kind of effect. So the boys' scores, again, a bidirectional hypothesis, we're not hypothesizing they're going to be higher or lower, are not equal to the girls' scores. They're different. So the null, they're the same. The alternate is that they're different. What type of t-test should she use for this analysis and why? Now you could use process of elimination. Well, there's 3 kinds. We've used 2 of them. Probably we're going to use the other kind that's left, but we want to be able to explain why. So in the last example, we had a paired samples t-test because we were looking at their change from pre-test to post-test. Now we're doing something different. We're looking at boys versus girls. These aren't paired up, right? Paired samples t-test, it's going to look like this in your data set. Here, if you have an independent samples t-test, which is what we're going to be using, right? That's the only one left. We're going to be comparing 2 groups that are not paired up. The boys and girls are not paired up in some meaningful way. So they're just 2 independent groups. Now again, you could have a situation where someone does pair them up. They say, okay, I'm going to take the lowest performing boy, pair him with the lowest performing girl, take the next lowest performing boy, pair him with the lowest performing girl, and so forth. But that's not what's happened here. These aren't paired up in any meaningful way. They're independent. So we're going to use an independent samples t-test. So Mrs. Mitchell should use an independent samples t-test. I put the T in italics. When you use an English letter as a statistical symbol, we put that in italics to compare the means of the 2 groups because the boys and girls are 2 independent groups. and they are not meaningfully paired up in any way, right? That's why. Run the analysis in SPSS and paste the output here. So we're going to go to Analyze, Compare Means, Independent Samples t-test. So we'll click on that, and it's going to ask for a test variable and a grouping variable. So what is the variable we want to test? Make sure you choose the right variable. I'll make this a little bit wider so you can see. It has the label and then the variable's actual name. So scores from the first time pretest? No, that's not what it's asking for. This is specifically asking for the post-test scores. So that's right here. That's our test variable. We're going to move that over here. Then it's going to ask for the grouping variable. So what are the two groups that we want to compare? We want to compare genders. We bring that over. Notice it says gender question mark, and then it says define groups. So you have to tell SPSS which two groups you want to compare. Even in this situation where there are only two groups to compare, there's boys and girls, males and females, there's only two groups, SPSS won't figure that out on its own. You have to tell it, right? Because there'd be situations where you have multiple groups, more than two groups. If you want to see if the resale value of two different colors of cars is different, and you have red, black, brown, white, and blue cars, and I just want to compare blue and red cars, you tell it, compare the red, compare the blue. In this case, there's only two options, but we still have to tell it that. So we're going to say define groups. Now, we can't put in male and female, right? It won't even let you. I'm trying to type the word male, and it's just dinging at me. You have to put in numeric values. Well, numeric values, what do you mean? Male and female are just two different groups. There's no numbers. Remember that these variables have been coded. We coded male as 0, female as 1, right? Do you recall? You can toggle this, right? Male is 0, female is 1. Sometimes you might forget, and that can be a problem because now you have to go out of the analysis you were just about to run and go back and check. But if you wanted to do that and you wanted to check, you'd go back to the variable view, click on the variable, or find the variable, and then click on under values, and it will tell you how they've been coded, 0 and 1. So that's the information I need in order to run this analysis. So analyze, compare means, independent samples. Again, I'm going to take that second variable, post-test, put it in the test variable box. Gender is my grouping variable. Define groups, 0 and 1. Continue, OK. All right, now this is going to give me two tables. We have the group statistics. Again, that's just descriptive statistics. We have the average for males and females. The sample size, look, this is smaller, 8 and 8, because there's 16 total, half are boys, half are girls. So we have 8 boys and 8 girls. The mean for the boys is 78.63. The mean for the girls is 85.13. Okay, interesting. So 78.63. So the female scores are higher. How much higher? They are about 6.5 points higher. Interesting. We know that the standard deviation for the full group, if I go up here, let's see, the post-test is 13. So it's about half a standard deviation, which would be right at effect size of about 0.5. That's a medium effect. So the girls are scoring medium better than the boys. But is there a statistically significant difference? We're going to look at the table down here. Now this table is a little more complicated than the other tables because it includes an extra statistical test. Levene's test for equality of variances. So one of the assumptions of an independent samples t-test is that the variances of the two different groups are statistically equal. If they're not, there's a small correction that you would do when you calculate your p-value for the actual t-test. So these first cells right here have to do with Levene's test. F of 1.6, significance level is 0.215. Because this is over 0.05, the two variances are not significantly different, so the assumption is supported. So we're going to use the first row, equal variances assumed, when interpreting our results. So this is another very common mistake that students make when they run an independent samples t-test, possibly the most common mistake, so please pay attention. This test, the significance value is different from this one. Now in this case they happen to be similar, but they typically won't be. When you interpret your t-test, you're interpreting the information over here, not over here, not Levene's test. That's just testing an assumption. We're moving past that. The assumption is supported, and we're going to interpret the p-value over on this side. So don't get mixed up. In fact, what we're going to do is I'm going to paste this over here into my document, and I'm going to actually crop it so that we don't even see Levene's test to aid in our interpretation. And we'll end up using the first row because the test is not significant, the variances are not significantly different. That is, the assumption is supported. So I'm going to crop out Levene's test altogether. I'll even crop out that title. And I'm going to crop out the bottom row because the assumption is supported, and then make it bigger. Here is the information that I want to be looking at. Put a little box around that. Do that up here too. Why not? Be consistent. So this is the data we want to look at. This is the output. I don't want to look at Levene's test anymore. That's done with. Just look at this and interpret this. So based on your analysis, was the difference between boys' scores and girls' scores, was it significant? What was the difference? Will we reject or fail to reject the null hypothesis? So let's take a look here. The p-value is 0.24. To be statistically significant, that must be less than 0.05. It is not. 0.24 is bigger than 0.05, so we do not have statistical significance. So there was no statistically significant difference between boys, should be plural possessive, post-test scores, and girls' post-test scores. Comma, space, T in italics, in parentheses we have the degrees of freedom, which is n minus 2, because this is an independent samples t-test. The calculation of degrees of freedom is slightly different, but it still gives that right there. Space equals space, 1.2, rounding to the hundreds place, 3. Got rid of the negative, not important. Comma, space, P in italics is not less than 0.05, not less than 0.01, not less than 0.001. So because this is greater than 0.05, don't do this. Don't do P is greater than 0.05. Don't do that. Say P is equal to 0.24. This lets your reader know that P is not statistically significant, but it also tells them by how much. Right? Some people are putting P equals just for everything, even if it is statistically significant. Most folks are still using the P is less than, but here it's more than 0.05, so we're going to put the precise value, again, rounded to the hundreds place, P equals 0.24. Should we add the effect size? I think it would be useful because it was still a medium difference, and the reader might like to know that. So comma, space, D in italics equals, so we're going to calculate the effect size. So the difference was, I believe, 6.5. We're going to divide that by the standard deviation. So the standard deviation for post-test scores, so this gives it to you both groups individually. We want the pooled standard deviation, which we found up here somewhere. So post-test scores, standard deviation is 10 point, oh, I think I was looking earlier. I think I looked at the first one. So this is actually what we want right here, 10.776. Right, because this is post-test, the pooled standard deviation for post-test is going to give us an effect size of 0.60. It's actually a little bit bigger than we originally thought. D equals 0.60. So that is a medium effect. So substantively, yeah, the boys did seem, their observed score was, substantively significantly lower than the girls, but it wasn't statistically significant. So statistically, the boys and the girls were tied. You don't have to report the effect size here, so if you didn't, it would just end like this, but the effect size can certainly be useful and add helpful information. All right, well, hopefully this was helpful to you. We've practiced all three types of t-tests. Make sure to pay attention to all of those details when you do this independently. Make sure you select the correct test, run it correctly, right, with the right settings, and then interpret it correctly. We're paying close attention to the p-value, the significance level. We're looking to see whether that is less than 0.05. If it is statistically significant. And we're going to report that according to the next highest cutoff point. And we're also, in this case, we've taken a look at practical significance as well, our effect size. Hopefully this is helpful to you, and that you will be able to be successful as you work on these types of problems independently. Thank you.